Hello everyone, I'm Charles. Today I'm going to talk about the new schemes for positional and motion tracking in virtual reality. Let me first show you a picture. You see, Mark Zuckerberg is smiling walking into a meeting room with hundreds of people putting on their VR headset. But you also notice that the man in the middle is not very happy. That is probably because he's not able to move freely in the virtual reality space. In fact, recent VR user studies shows that some people argues the motion parallax is actually more important than stereo vision in perceiving 3D in virtual reality. So in order to make everyone happy, we really need to include positional and motion tracking in your VR devices. But the real question is, how would you do tracking in such a big room? Let's review some of the tracking technology we have discussed in class to see if that works. The first is Oculus DK2. What they used for tracking is to put arrays of IR LEDs on your headset and use an exterior IR camera to detect the movement of those LEDs. But as many people putting on their headset together, it is impossible to identify which LEDs we are looking at, so this game wouldn't work. Another tracking technology we have talked about is HTC Vive's tracking scheme. What they use is to set up 2 lighthouse stations in a room, and by sending out the spatial pattern, you know your position. But according to HTC, their maximum detection range is only 15 and 15 square feet. So it wouldn't work in a meeting room either. What you really need is a new scheme that enable every user can do the tracking themselves individually in a big environment. The new scheme I will introduce to you today is Google Project Tango. The general structure is very simple. What they use is an IMU, or the inertial measurement unit, plus a fish eye camera that is mounted on your VR headset. And a fish eye camera is just a simple camera with a very big field of view. To do all the orientation and motion tracking. So you see, in this game you don't need any other exterior devices to help you do the tracking, such as the IR camera or the lighthouse station. What you really need to have is just an IMU and a camera. So you can also do that in your mobile VR on your smartphone, which is a really great advantage of this new scheme. And beside these 2 tracking sensors, you also have a TOF camera, which is used for the 3D reconstruction in computer vision. So how would you do orientation and motion tracking with just 2 sensors? Let's start with the simple one, the orientation tracking. It is accomplished by our old friend IMU sensors. So you know the IMU comprised of three sensors, which is a gyro, an accelerometer, and a magnetometer. To get orientation of your VR headset, what you basically need is to measure the three angles of pitch, yaw, and roll. You know, you can get these angles from gyros only, but you know the gyro have an integration process to get the angles, so you kind of have a linear drift of your measurements. To compensate for the linear drift, people use a technique called sensor fusion. More specifically, in this case, people use the 9 degrees of freedom sensor fusion. So basically, you combined all the 9 measurements of your gyro, your accelerometer, and your magnetometer to get the final angles. So how does sensor fusion works? The idea is actually very simple. You have your three angles, pitch, yaw, and roll. You can have those three angles from your gyro measurement only, and it turns out that you can also have the pitch and roll angles from your accelerometer measurement only. And that is because when your device is in a static or near static state, your accelerometer is always measuring the gravity vector. So if your devices have some kind of rotation, from the measurement of your accelerometer, you can determine the rotational angle. But because you know the g vector is parallel to the yaw axis, you cannot do the sensor fusion for the yaw angle. And to do the sensor fusion for the yaw angle, you need another sensor, and that is a magnetometer. So similar to the accelerometer's ways of sensor fusion, when your device is in a static or near static state, you are measuring the magnetic field of the geomagnetic field. So if your devices, you know, have some kind of rotation, you can also determine the yaw angle from your magnetometer's measurements. So after or when you combine all the 9 degrees of measurement of your gyro, magnetometer, and accelerometer, you kind of have a more accurate yaw, pitch, and roll angles. So that is the basic concept of the sensor fusion. And of course, when you combine these angles together, you will need some kind of filtering, like the complementary filtering or the Kalman filtering. But you know, as we are going to talk about a more interesting and more challenging topic, so we are not going to jump into that much technical details. Compared to orientation tracking, the motion tracking is much more difficult. That is because you know the angle you get from your gyro measurement only have a linear drift, but the position you get from your accelerometer actually have a quadratic drift, as we talked about in class. And it is really challenging to compensate for this quadratic drift of the positional measurement just by the IMU. So we need some extra help. So Project Tango uses a fisheye camera to compensate for the quadratic drift of the positional measurement. And the technique they use is called SLAM, which stands for the simultaneous localization and mapping. The SLAM technology is originally developed in robotics and computer vision. It aims to help our robot to recognize its position and its surrounding environment without any prior of the environment. To better understand SLAM, let's look at the pictures. So I will introduce some of the notations here. K is the time constant, and the xk you see here, and here is the robot state vector, which stands for the position and orientation of the robot. And we have mj here. Mj is our landmark vector, which stands for the position of the landmark. And we also have the UK here. UK is the control vector, which drives the robot from one place to another place. And we finally we have our DKJ, which is observation we make at a certain time K to a certain landmark J. And we also have the notation of the U0K, that stands for the set of UK, and we have the D0K that stands for all the observation set. So the SLAM problem can be described as a probability estimate problem, that you want to estimate your robot state as well as your landmark's position simultaneously given your control vector and your observation. To solve the SLAM problem, people have developed a two-step iterative algorithm. So first, you do a time update, and second, you do a measurement update. These two formulas are derived by the Bayes equation. I'm not going to show you the details of the derivation, but I do want to point out two very important expressions here. So first one is called the motion model. So the motion model describes that given a control vector, how does your robot is going to move from one place to another place. And in our VR case, this model can be measured by our IMU data. Another very important expression here is called the observation model. And the observation model is basically described that given a robot position and given a landmark, what is your observation is like. And in our VR case, similarly, we have our camera to take the images of our surrounding environment, so we can have this observation model from our camera. So in conclusion, to solve the SLAM problem in the positional and motion tracking, we have to combine our IMU data and our camera data to get the position of our robot, or in the VR case, our users, and the surrounding environment. In the end of my presentation, I want to give you guys an intuitive sense of how well Project Tango is doing its tracking job. And this demo video is actually presented on Google I/O last week. Let's enjoy.